Hi everyone, great you're here again. After yesterday's launch with Worley on quantum computing, Noel Goddard on quantum communication, and then the start with QWorld on QKD and quantum computing and programming, we're back today and great to have you back. Today we will introduce a new topic. Not only quantum computing is the quantum technology of the future, but also quantum sensing, and this has even nearer term applications. For that purpose, we have with us here Nicole Metje. Nicole is a professor of infrastructure monitoring and the director of the National Buried Infrastructure Facility in Birmingham. And maybe unexpected for some of you, Nicole is a civil engineer by training, and still she is a pioneer in quantum. Why? To reveal the invisible below the ground surface, you need sensors, and what can eventually be better than quantum sensors? Nicole and the team are developing quantum gravity gradient sensors, and in this talk you will hear everything about it. We welcome your questions on Discord, and with that, let's kick it off. Nicole.
Thank you very much. Thank you for the introduction. I'm really delighted to be here today. It's probably good morning for most of you, but also good afternoon, good evening, wherever you are listening to this. I'm really delighted to be here to talk about quantum technology, gravity sensing. Before I go into detail what we're doing here and what sort of the research is, I just want to give you a bit of background about myself. So I graduated at the University of Hanover in Germany in 1998, so quite some time ago. I then did a PhD at the University of Birmingham, that's in the UK, Birmingham, UK. This is 2022, that just shows that I've nicked a slide from somewhere else, that should be 2002. That was actually in coastal engineering. So my aim has always been to save one of the North Sea coastal islands called Sylt in Germany, because that suffers from erosion processes. So that was the grand vision, the aim. But I also had an interest in tunneling and this sort of below the ground, anything you can't see, anything that's challenging where you have to work with nature. So I then did my postdoc at Birmingham. That was more in terms of the below ground, your pipes, utilities, and I'll go into detail a bit more in a bit what that means. But I've been an academic for quite some time now, as you can see, and I became a professor in 2018. So I've always been at Birmingham, which has pros and cons, but that's probably a different presentation. But first of all, let me just show you the sort of thing I'm doing and where I'm coming from. As I said, my first degree is civil engineering, and I always say if you'd asked me 15 years ago, do I know anything about quantum technology, I probably would have just laughed at you and said, well, nothing to do with civil engineers, is it? Well, let's think again and actually see why it is important for civil engineers as well. This is the sort of thing that I do. I look down holes. Whenever there are excavations, I take pictures, and these are quite a lot of pictures that I've taken. And what you see here is pipes, cables, because where does your water, where does your broadband, where does your electricity, where does the gas come from? Most of the time we hide it below the ground surface because we don't want the pylons in our backyard. Also, it protects it a bit. But one of the problems is it's in the ground for a long period of time. And at some stage we might have access to it to repair or replace it. You can see some breakages in the middle picture and the top picture. You see this is a cable through and the duct is broken. There's another duct broken here. We get pipe leakage. So we need to access it. But also whenever we operate in the ground, we probably need to break the ground. And the first thing we hit is our cables and pipes. And clearly we want to avoid this because we don't want any service disruption. But what else is in the ground? We also have sinkholes. So these can occur due to a number of reasons. One of the reasons is that there is old mine working and there's an old mine shaft and then it opens up. It could also be as a result of what's called a solution feature. So what does this mean? This basically means that some water as a result of a leak in a pipe has washed out some material, and then the road that's above it, and if you have a hole underneath, it doesn't have the support and it then collapses and you get something called a sinkhole like you see here. This is quite a big one. It's in the city of St. Albans, sort of near London. But as I said, these are old mine shafts. And the problem is we just do not know exactly where our mine shafts are. We don't know exactly where our pipes and cables are. it might be really surprising. Why is this the case? Well, the reason is that these are quite old. So some of the mine workings we have in the UK are 100 years old. Our pipes and cables are 150, 200 years old. We still got Roman sewers in the ground in London. So we're talking about assets, so our sewer systems, our tunnels, that are 1,000 years old. So not surprisingly, we don't really know where they are. So the other thing that we find, as I said, is our mine workings and the mines. But if I want to create something in the ground, I want to dig a hole, I really need to know where this is, because I need to de-risk any hole digging. I need to make sure that this is safe and we can do it cheaply, but we can also protect everybody who works in that environment. But this is a sort of the challenge, but there's also huge opportunity. So just think about what can you do with the below ground surface. You can see here you've got some underground infrastructure. So this is a tube. This is, for example, in London, or a metro station or metro. You've got road tunnels. But you also, more and more, you do it as energy storage. So this is gravity energy storage. This simulates our ground source heat pumps. We're going away from using gas to heat our houses. So we want to use the thermal capacity of the ground to heat our houses. Here you've got data centers. Why is this important? Because the ground has a reasonably good constant temperature throughout the year. So the temperature varies very little. So this is a suitable area for data centers. You can also imagine that you've got shopping malls, offices below the ground surface. If you think of cities such as Toronto or Singapore, there's a lot more underground malls than in other places maybe. And that's because of that extreme weather. So Toronto because of the extreme cold, Singapore because of the extreme heat. But anything you can put below ground, what it does do, it actually opens up your surface infrastructure and you make it greener, more parks, more surface water, and that actually is better for living. So that could be really nice as well. So really knowing what's in the ground already and how we can operate in this space, this third dimension, is really vital. So that's a bit of the background. Coming back to what we normally do to look through the ground. Well, one of our most common tools is an excavator. We literally dig a hole and we look at the material. We can test it in the lab. We can also drill boreholes. So these are cylindrical boreholes. And again, what we want to do, we take samples out of the ground and we tend to test it in the laboratory. That gives us a lot of information for that specific area, but it doesn't give us very broad information. And you have to dig it up. So just digging it up in the first place, you have to watch out that you don't hit anything and you don't damage anything. An alternative way of doing it is using geophysics. And this is where the quantum side comes in a bit more. So what you can see here, you can see some classical geophysical equipment. Down here is something that's called a ground penetrating radar. There's another ground penetrating radar here. But this little box is an old CG5, so that's a gravity instrument. And just remember the size, remember what it looks like. And this is what I will spend a bit more time in a minute talking about. We can also do something like what we do here is conductivity. So the different ways where we can walk around the surface to try and look through the ground. But clearly it's only a proxy. This is so unlike when we take the samples where we can see it. This is a proxy where we're trying to see what's in the ground. But ultimately, we're trying to put a picture together to really try and understand what's there. So how do most of the geophysical techniques work that are not based on quantum technology or indeed gravity, which is what my talk will focus on in a minute? Well, most techniques send an electromagnetic wave through the ground. So you can see this on this picture. This is simulating a ground penetrating radar. We send a wave through the ground. That wave gets reflected of whatever is in the ground. In this case, it's a pipe. It gets reflected, travels up to the surface. This will move along and it will actually measure that reflective wave. But the ground is really complicated. I know it doesn't sound like it, but you've got your soil, your solids, you've got air, you've got water in there. And often it's the water that affects this electromagnetic wave. And what that means is that my signal doesn't go as deep as you might like it to go. And again, think about What depth are pipes? Well, in the UK, they are probably at about 1 meter below the ground surface. In the US, they're often deeper because more extreme weathers, so probably 3 meters. We've got our mine shafts, they could be 5 to 10 meters, some shallow ones. We do have our metros. They again can be between, I don't know, 5, 10 meters if it's really shallow. So in London, we do actually have some underground tunnels that are really shallow, 5 meters below the ground surface, or you can have them a bit deeper. But for this, we really need to have a signal that penetrates deep into the ground. So here you can see what I've just said. So you've got the solids, that's your sand. In this case, it's your sand. Here you have got your clay. So clay particles look very different to sand. So you've got these very fine particles, much smaller, but you get this layering. And you've got the water. So these are your soil grains. You've got your water. So in this case, there's no air in it because all the air is filled with water. But the bottom line is all of this affects how far my signal can penetrate through the ground. So one of the options we have is to use microgravity. Gravity, similar to magnetics, is a passive technique. So that doesn't actually send an active signal through the ground. It just measures what's there. So in terms of microgravity, it measures a variation in density. In terms of magnetics, it measures a variation in the magnetic field. So when I look below the ground surface, is that the different materials in the ground have different densities. So they weigh different, they have different masses, basically. What we're really trying to do when we use microgravity in engineering applications, we look at a change. So we take a field measurement. So we either do a grid or we do a line over a suspected feature, and we try to measure what's the relative Earth gravitational field. So what is a gravimeter? So a gravimeter or gravity meter is a highly sensitive instrument, and it measures acceleration due to gravity. So here you see a classical instrument. You've got a mass here that sits on a spring and it gets pulled down. So this is akin to Newton's apple. So you can remember Newton's apple falling from the tree. So if there is a really heavy mass here, this test mass gets attracted by that mass in the ground a bit more. And if there's a void, such as a pipe, you might get a void here, it gets attracted slightly less. So I'm not measuring capital G, I'm really interested in the variation in small g. So I've already said this, what happens when I'm positioned over a dense material or a low density feature. But one of the problems I have is that it measures an average value with depth. So I then have to use my engineering judgment, my physics, my computer science to really interpret what the measurement actually means. And that's really complicated, but it can be done. And advances in machine learning, advances in artificial intelligence all help with this. But again, this could probably be a talk for another day. So basically, having looked at all existing sensing technologies, what you can see is that there's a zone here where quantum technology, gravity instruments might be really useful. So all this is where other instruments might detect it. So on the x-axis, you see the diameter of the feature. On the y-axis is the depth. And what you're interested in is this area where none of the existing sensing technologies really work. So here's a picture of a more modern instrument. This is called a CG6. It's a classical instrument, and you can see it as it's in gravimeter. This is just a gravimeter. But you can actually buy a stand like this, where you can set up up to 3 instruments as a gradiometer configuration. And here in the pictures, you see the equivalent quantum instruments. This is the sensor head for our gravimeter, and this is the sensor head for our gravity gradiometer. You see the size difference, and it also comes with a big flight case and an umbilical cord. This is an older instrument. This has actually changed a bit, but the principle is still the same. We have a big sensor head, a tall sensor head, and we have our flight case. We need that tall sensor head because we have two atom clouds. So what's the difference between the quantum instrument and the classical instrument is that the quantum instrument doesn't use a physical, it uses rubidium atoms in our case as the test mass. That's really fantastic because they're always the same. They always have exactly the same mass. And rather than using a spring, we use a laser as a ruler to measure it. And we're using a gradiometer. So most of the time we're using this instrument because we then have two measurements. And one of the problems we have is that because gravity is an accelerometer, so it measures acceleration. And acceleration could be as a result of wind, could be as a result of tree roots moving, so trees moving, that translates into tree roots, translates into vibration in the ground. Could be ocean waves crashing on the shoreline. We can measure this, but this is all noise for us. We don't want this. So having the two instruments, having the two clouds, sensor clouds, we can take the difference and subtract it. So this is what this picture shows you, that in gradiometer, when we have dual sensors, it's much better than having a single instrument for our application field. So here you can see, I'll play this really fast. Here you see an old classical instrument, and you can see it's quite slow to move. So this is along a railway track. We were looking at a culvert and trying to find where that culvert is. One of the things that's really critical is that we align it vertically, so it has very low tolerance to tilt, and therefore it takes quite some time. If you watch the timeline, we've probably done about 20 meters in 2.5 hours. And there's lots of standing around. But what did we do here? What did we measure? We tried to find this culvert. So this is a drainage channel that goes under an embankment for a railway line. We tried to see this. And this is our gravity signal. You can sort of assume it's here, especially if you know where it is. But there was also an underpassage that was filled in. Nobody knew about it. And that gives you a significant gravity low in our measurements. What we also do, so this is trying to find buried assets, but I've got a new project called QS Games, where we're looking at using our gravity instruments and other geophysics. So this is a ground penetrating radar, our quantum instrument, a classical instrument, combine that with artificial intelligence and machine learning to look at changes in groundwater level. That could be as a result of changes due to climate change, could be as a result of a leaking pipe. But really what we need to know is where our aquifer level, so where's our groundwater level, because we use that for drinking water a lot and companies really need to know. So this is moving into the sort of earth science and environmental science area as well. So completely different area from the sort of classical civil engineering aspect. One thing I can't do, I can't stop a presentation without telling you about our fantastic test site that we have. So this is what's called the National Buried Infrastructure Facility, which is a new facility opened last year. And really you can do control tests and it allows you to do at scale. If you ever want to play with soil or sand, this is your facility to do so. And here are some more pictures. You can see the scale. So this is 25 meters along there, 10 meters across and 5 meters deep. And this is already filled with soil. And what I'm going to show you on the next slide is when the quantum instrument was here. So here again is a newer version of the quantum instrument, still with its sensor head and its flight case. And what I really want to show you is that video. So you can see this video is also on YouTube or so, but what this led to all this work is that we actually have a tunnel on campus. So this is not in the lab, this is a tunnel on campus. And we had our sensor around, these are buildings either side. We moved our sensor across and we could actually detect this. And what's really fascinating that for me personally, that this ended up also demonstrating what other application areas we have. So there are quite a few here. I'm realizing I'm a bit tight for time. So there are quite a few application areas shown here. So we're not just looking at infrastructure, which is sort of my area, but also archaeology, agriculture, navigation. But what's the key is that this led to a paper. This was published in Nature. But I don't think we could have published this paper had it not been for the collaboration between industry, academics from civil engineering and academics from physics. And this led to this really, well, it's an international or world first demonstrating that we can take the sensor out in the field and detect a buried feature. Before I conclude, here's just occurred to me that some of you might be really interested in PhD opportunities. We currently have a PhD opportunity open. As you can see, it's called Revealing the Subsurface, Creation of Real-Time Gravity Maps for Engineering Targets. This is available on Find a PhD. I've put the link in here as well, but this is just the screenshot of it. If you're interested, we probably have another opportunity in the quantum field in the combination with engineering, more the environmental science side, but also the physicist. Do send me an email and talk to me. So in summary, what I probably haven't emphasized too much is this working across disciplines is fun and it allows us to think outside the box. I really enjoyed working with our physicist colleagues, and as I said, we've achieved things I don't think either of us could have achieved on their own in that time frame. But it's also really exciting challenging each other and knowing more about other disciplines. For me personally, the unknown ground conditions pose a real risk when we do any civil engineering construction. We have a suite of sensors, so a suite of geophysical sensors that we can use, but we don't probably use them to their full potential because it's still expensive, especially for gravity sensors, they're expensive and slow. The quantum technology gravity gradiometer sensor could make a real difference because it can do things much faster and has an improved sensitivity. The improved sensitivity allows you to detect something that you can't currently see. So it's either smaller or deeper. We've demonstrated the world first gravity detection of a buried feature. This was what's called a multi-utility tunnel, but again, that's probably a different presentation. But really, what we do need to do is we need to reduce the size, weight, and power and speed up surveys. And this is something we're currently doing as part of our Quantum Technology Hub Phase 2, and also doing in lots of parallel projects. I think that's all for me. I'm really delighted to have been here and to give you a brief overview, especially as it's probably the odd one out presentation for most of the things you're going to hear or have heard about yesterday and are going to hear about today. But all I can say is no matter what's your background, they're really fascinating things, and there's always a place for everybody in the field of quantum technology. Thank you very much.
Thank you very much, Nicole. This was really amazing presentation, illustrating that quantum is not only quantum computing, although quantum computing is really exciting and promising. There are very direct applications in the broader quantum field, and people from all kinds of backgrounds are extremely important. Civil engineers, electrical engineers, computer scientists, also business people. Everyone is needed in the quantum field. There are really lots of questions. I will start asking and make a selection. They have been asked on Discord, and everyone, please keep on asking. We will share important questions later on also with Nicole. There are several questions about the advantages and resolution. Akash from India asks, what advantage does the quantumness give, which is not seen in classical detectors? And Juliana from Italy asks, with classical gravimeters, you can obtain a precision of 0.1 milligal. What are you able to obtain with quantum gravimeters or gradiometers?
So in the field instruments, the classical one doesn't give you gives me around 5 to 10 microgals. So that's even better than 0.1 of a milligal. But what we are aiming is that we can get it down to 1 microgal, but because the key advantage is that we're looking at the gradiometer configuration. So even with the classical instruments set up as gradiometer configuration, they are not tied to the same common laser, basically. They all have their own spring constant. They vary slightly. So the instrument noise varies slightly. So they can't suppress common noise as ideally as the quantum sensor. So what we are aiming for is that we end up with one EDVOS for the gradiometer and one microgal for the gravimeter. But one of the key things from a civil engineering viewpoint is also the speed. So the aim is to be 10 times faster, which means you can either cover the same area 10 times as fast, or you can cover 10 times the area at the same time. And that's what costs a lot of money for surveying companies at the moment.
Can you share a bit more about how the quantum sensor really works? How does it work with the clouds of rubidium atoms in comparison to the spring?
Yeah, it's always interesting that the civil engineer gets this question and not the physicist. So let's just go. We have one cloud of atoms. They are trapped with lasers and a magnetic optical trap. What we then do is we kick them with an energy pulse. They separate into two different energy stages. We then kick them again with another energy pulse. They come together. They are in free fall in their two energy stages. They're in free fall. They come back together, and we're measuring the interferometry using that common laser. That's probably the best I can do in 1 minute or 30 seconds, but that's very different to the classical instrument.
Yeah, and I think it's a much more accessible explanation than many physicists would give. This is great. We will also share the papers that you have on it, in which it is really clearly explained. Can you share more about the challenges that are coming up to make the technique really widely applicable?
From a practitioner's viewpoint, the biggest challenge is that they are currently not waterproof. And when I work in the field, I don't have lovely sunshine most of the time. So, but that is a problem that can be solved. But and probably the size is the other problem. But you've seen some of the drill rig on one of my earlier slides. So in civil engineering, we are used to having quite large instruments on site. So that's not the biggest problem. But it's obviously also the cost, because these are not commercial instruments at this stage. So if you want to buy one from the University of Birmingham at the moment, I think you need to have quite a lot of money. Whereas we're obviously hoping that that comes down to being more akin to the classical instruments. So the classical instrument costs around, what is that in US dollars? Around 120, 130,000 US dollars. And that's a sort of price range we're aiming at, but then maybe even coming down to be more akin to a ground penetrating radar, which can be between 15 to 50,000.
Some people are thinking ahead. Yes, from India asks, can we come up with a similar technology to explore the depth of the oceans? What are your thoughts on this?
So I think the answer is yes. So some of my colleagues have utilized a quantum technology gravity sensor in space. So there's space applications, and because if you can change the variation in mass, so what we're looking at is looking at flood inundations, for example. So when you've got large areas flooded and you suddenly have water on the surface, to measure that. So it's always measuring change is what we're interested in.
I really appreciate also your engineering perspective. As a physicist, we don't often think, is something waterproof, or have the very specific applications instead of the broader ones. And this is eventually to bring the science and tech to the market. It's very important. We will have a talk on Friday by Marlou, who will also give the systems engineering perspective on quantum sensing. I hope that you will all be there. The questions are going on. Let me see for one last one.
Maybe I can take one last one. Yeah. Nicole, I'm curious as well, the data you've been collecting, and any good researcher will ask you, can you please share the data with the larger community and they can come up with their own analysis?
So there's some data that is shareable, other data is not shareable because it's done through an industry funded project. So it just always depends. But I think, again, the best thing is to contact us.
And then the very last question, how do you see collaboration with quantum computing scientists? Will quantum computing be useful eventually for the quantum sensor?
I mentioned very briefly that inversion, the non-uniqueness is a challenge, and the inversion is a challenge. And I think for that, if we start collecting more data, which is what the new sensors will enable us to do, I think then the inversion processes using AI and machine learning will possibly benefit from quantum computing. I mean, sure, they benefit, they will be faster. It's just whether that speed is worthwhile for the application, if you see what I mean. So at the moment, what takes the longest is the collection of data. So we can be out on site for 3 weeks and then analyze it for a week. So if we can bring down the data collection, that will save a lot of companies a lot of money, and will make gravity surveying a lot much more likely tool to be used. So but I think it's with all of these things. At the moment, we have limited data because it's points with quite long spatial or with a low spatial resolution. So if we can increase our spatial resolution, then we need more advanced processing power tools, and that's probably where quantum computing does come in.
Amazing. Thank you very much, Nicole. I would like to share a few comments from everyone here. Shima says, it was a wonderful presentation. Thank you for showing a real-world application of quantum. Thank you, Nicole. Mohammed says, thank you for the presentation. It was really interesting and opened my eye to the fully new field of quantum sensing. Thank you very much, and we would love to welcome you back for even more discussions and talking about quantum sensors. Thank you.
Absolutely. Next time, pick a time when I'm not on annual leave, then we've got plenty of time. But no, it was fantastic. I really enjoyed it, and I think it's important to show that there are so many different areas that can work with quantum, quantum technology.